Hey guys, so in this lesson what we're going to look at is combining the stuff that we looked at with torque. Torque's a relatively easy concept. It's a perpendicular component acting on an object that causes it to spin. It's a force times the distance to the pivot. It's not, I don't think, very difficult to see how it shows up in the everyday world, but to see how the implications of it though are fairly wide-reaching. Shall we say. So we're going to look at applications of that today. We're going to combine the stuff that we looked at with torque with the translational equilibrium, like the forces up and down being balanced, forces left and right being balanced, and see how they apply to a whole bunch of different kinds of problems. So here we go. So translational equilibrium, So translational equilibrium doesn't move up, down, left, or right. That's how things get, that is what translational movement is. Rotational equilibrium doesn't spin. So you want to look at objects that have both sets of equilibrium and see how that happens. So is it possible for an object to be in translational equilibrium but not in rotational equilibrium, i.e. It's not moving up, down, left, or right, but it is in fact spinning? I'm hoping that answer is obviously yes, and I can think of a couple examples just kind of off the cuff here. One example is a Ferris wheel. I know that might be a bit of a stretch for some of you if you've never been out to Playland or been on a Ferris wheel. The thing is spinning, but it's not moving in any left, right, up, or down sort of sense. I'm hoping this one is a little bit more familiar with you. I'm hoping you wash your clothes. Your washing machine, same kind of deal. It spins, or this way, the drum inside, but the washing machine itself is hopefully not, moving across the floor wherever it is you live. So some examples. So we got some diagrams here. We want to show, we got some beams. They're sitting on a frictionless table. So we're looking down on these things. The tabletop would be like the page. So gravity is into the page. Normal force would be up out of the page. We want to specify the type of equilibrium each beam has, whether it has translational equilibrium, rotational, or both, or neither. For torques, we want to take the pivot to be at the center of mass, and these things are uniform, so we're going to assume that the center of mass is actually the center of our object. So if we look at what's going on here, if this is the center of mass, these two forces would cause this thing to spin. Like if you imagine what's going on here, lay your pencil down on the page and then just push. Okay, the thing spins. The pen itself is not moving up and down the page, so this thing has just translational equilibrium. Let's go over here to this guy. I put my pen down there and I push and I pull. Okay, this guy has rotational equilibrium because it's not spinning. This guy, if we look at what's going on here, this guy's acting at the pivot. So it doesn't have rotational equilibrium, but it does have translational. It doesn't move up the page, but it spins. That's translational, EQ. And then this guy here, if you imagine what's going on here, we've got a 10 upwards and then 10 downwards. This thing's not spinning, it's not moving up and down, it has both forms of equilibrium. Okay, relatively straightforward. Let's look at some problems now that deal with this. Okay, so we've got a 100-gram meter stick. We're told it's in rotational equilibrium. That's important. The implication there is that my torques clockwise equal my torques counterclockwise. That's going to be useful to us. The numbers above the stick represent centimeters along the stick from the left end. So this is 15 centimeters. That's 50 centimeters, so that's right in the middle. And this is 95 centimeters. That's where that guy's hanging from. So this guy over here is obviously going to be 0. This thing here, this 100 grams, masses always need to be in kilograms, so let's convert that right away. That's going to be 0.1 kilograms because there's 1,000 grams in a kilogram. And this thing's measured in centimeters. We don't want centimeters. We got to make sure we need meters. Okay. So let's actually go through and figure out what we've got here. So let's just do some converting right away. 15 centimeters is 0.15 meters. This guy here is going to be 0.5 meters, and this guy here is going to be 0.95 meters along the meter stick. We're given a pivot point already at the center of mass. This guy's hanging here. We want to know what this mass is. The question says, find the missing mass required to balance the beam. Okay? So we know a few things. We know that this thing's in a rotational equilibrium. It's also going to be in translational equilibrium and things not moving up, down, left, or right, but that's not going to be super useful at this stage, let's just get started and you'll see how this works out. So, free body diagram. We need to draw some forces on here. So I'm going to grab green. This guy has Fg downwards. Remember, that's 100 grams, so we have to convert that to kilograms. 0.1 kgs. So that's Fg of 0.98 newtons. 0.1 times 9.8. There's an Fg downwards here. That's just for the mass of the beam. We're told that the beam weighs 100 grams, so that's going to be 0.98 newtons as well. We're going to have an Fn acting upwards. We don't know what that is because we don't know what this is. This Fg here is just going to be 9.8 m. We don't know what it is. And so that's our free body diagram. Those are all the forces that are acting. So now we're going to add a few more things. We're going to look at we're going to draw in some torques, and we're going to draw in what direction we want to call positive. So this guy here, if that's my pivot point, if this is the only force that we're acting, it would spin the beam this way. So this torque is going to go that way. This torque is going to go this way. Let's call this way positive. It doesn't really matter. Conventionally, clockwise is positive. We're told that this thing is in equilibrium. Okay? They're not going to tell you that the torques are balanced. They're not going to say, oh, the torque clockwise equals the torque counterclockwise. They'll tell you it's in rotational equilibrium, and it's your job to understand what that means. So equilibrium means torques clockwise equals torques counterclockwise. So my clockwise torque is this guy here. And remember, the distance is always from the pivot. So this is going to be F perpendicular R is going to equal F perpendicular R. We'll call this guy clockwise. We'll call this guy counterclockwise just to distinguish between the two. And now we've got to fill these in. So the clockwise is this guy here. So this is going to be 9.8 m. And now the distance to the pivot, if that's at the 50 centimeter mark and that's at the 95 centimeter mark, the distance in meters between the two is going to be 45 centimeters, so 0.45 meters. This guy here is going to be 0.98 newtons. And then the distance is, the pivot's there, we're at the 15 centimeter mark here, so this is 35 centimeters here. 0.35 centimeters. So now we can go through and solve this thing for m. So m is going to equal 0.98 times 0.35 divided by 9.8 times 0.45, which is going to give us a mass of 0.078 kilograms, which is 78 grams. And we're done. Okay. That's it. Relatively straightforward, I think. Flip the page. We'll do... Yeah, we'll do one more full example, and then I'm going to do a couple, we'll kind of do some discussions about a few other ones that you can look at. We won't do them fully, but we'll talk about what it looks like, and then you guys are I'll give you some questions to do for homework here. So flip the page. Here we go. Ooh. All right. So until up to this point, the questions have always been pretty obvious about where the pivots are. They're at the center of mass, typically, but they don't have to be, and that's never been expressly discussed. So until now, all of the torque problems we have considered have had an obvious pivot point, the center of mass for the beam, or the middle of the teeter-totter, or the hinge on the door, or whatever. But there are going to be objects, situations that we look at, which are at rest that do not have obvious pivot points. So for example, we have this guy here. He's in a push-up position. He's planking. His arms on this. I know this would be a terrible plank, but his arms aren't on the ground. But look at that. Look at that form. Where is the pivot point on this guy? Like, where is he pivoting, or she? I mean, this stick person, where are they pivoting around? Are they pivoting over the feet? Are they pivoting over the hands? Are they pivoting around the center of mass? We don't actually know. And depending on your reference frame, you could look at them and pivoting at any one of those spots. If you had, I mean, there's videos on YouTube that you can watch about how there's image stabilizers. So if you stabilize on the center of mass, you could argue that that's what's remaining stationary and the person is pivoting around that point. You could argue that the feet are what's stationary and that they're pivoting around their feet. You could argue that the hands are stationary and that they're pivoting around their hands. So it doesn't matter where you put the pivot point in a problem like this, okay? As long as the object is not moving. So what you want to do, and the language that I've used here in the past, is you want to weaponize the pivot point. And what I mean by that is you want to use it to eliminate torques, right? Because if you put the pivot point at a particular location and there's forces acting on that point, now that the pivot is there, the forces aren't going to be considered to be providing a torque at that point, because torque is all about the force times the distance to the pivot. I'll show you what I mean here. You want to use it to eliminate torques to make problems easier to solve. So here we go. We've got example 4 here. The person in a push-up position below is at rest, and so is in rotational and translational equilibrium. Using the toes as a pivot, write a balanced torque equation and find F hands. So we're told to use this as the pivot point. So we're going to draw it in. Okay, and this is where these problems get difficult is the wrong word, but students don't like these problems typically because now you've been given freedom. The question won't say use the toes as a pivot point. The question will say find this force acting on this person, and so you have to be smart about where you put the pivot point, and the choice now becomes yours. You have to be creative about what's going on here. So this question specifically says use the toes as a pivot. So there's our pivot. We've got our forces here. This is F toes. This is going to be F hands. This is FG. And we are told this person is at rest. So there is total equilibrium. And the implication for that you guys are going to have to understand, I'm going to write it out here. And I want you to get into the habit of doing this. Total equilibrium means my forces up equal my forces down. This would also mean that forces left equals forces right, but there are no left and right forces here. It's always, so this one was just up and down. and my torques clockwise equal my torques counterclockwise. Okay? So we need all of this. So up equals down. Well, that means if the force on my toes and the force from my hands, this is going to be, my upwards forces are going to be F toes plus F hands. And that's going to equal my downward forces, which is just FG. Okay. We'll leave that there for now. We're going to go look at the things that are causing torques. Now, we were told in the question to put the pivot here. So the force from the toes, because the pivot is there, there is no torque here, because if you remember, torque is perpendicular force times the distance to the pivot. Well, the distance to the pivot is 0 at the pivot. So it's just these two forces that are providing torque. This force is going to cause the person to drop. So the torque here is going to be this way. This hands is pushing the person up. So the torque here is going to be that way. It doesn't matter which way you call positive or which way you call negative, so I'm just going to add in here that I'm going to call this way positive. Clockwise is positive. So then let's fill this thing in. We know that my clockwise is going to equal my counterclockwise. So F perpendicular R clockwise is going to equal F perpendicular R. Oh, whoops, that should have just been a C, W, C, C, W. So this is going to be FG times R is going to equal, we'll call this RG, the radius for the gravity force, is going to equal F hands, I'll call that RH. I don't know. I'm just using a way to distinguish between the two distances here. So FG is going to be 700 times, now the distance to the pivot is 50 centimeters. We want that in meters. So it's a half a meter, 0.5 meters. That's going to equal F hands. Now that's 50 and that's 30, so that's going to be 80 centimeters, which is 0.8 meters. At the same time, I'm going to go and plug some stuff in here. I know that F toes, I don't know the value there. I don't know F hands, so plus F hands equals 700. I do know gravity. I want F toes, so that's what we're going to try and solve here, equals 700 minus F hands. Don't know what hands is, but I can solve for it right here. I'm going to divide both sides by 0.8, divide by 0.8. It's going to cancel there. So I'm going to find that F hands is going to equal 437.5 newtons. I can plug that in here and find that the force on my toes is going to equal 700 minus 437.5. That's 262.5 newtons. So by placing the pivot here, what we got rid of was a torque from a force we didn't know, which made this solvable, which means we could plug it in here and solve for the force that we were missing. Okay? So what I'm going to do is I want you to go back up here, and so we're not just eliminating torques, we're specifically eliminating torques, I'll say for forces we don't know. Okay? That's how you want to use this. Okay. So we're going to flip the page. We're going to see the example 4. It's called 4C, but the next example, and the only difference is it places the pivot here. So flip the page. Solve for F toes by writing a balanced torque equation with the hands as the pivot. I'm not going to do this one fully, but I'm just going to show you how this one would work. If I put the pivot here, now what I'm doing is I'm eliminating this. My torque equation, torques clockwise equal my torques counterclockwise. So if my pivot is here, I got F hands. I'm not going to do all of it, but I'm just going to show you kind of quickly what this looks like. F toes and FG. Now if my pivot's there, this force is going to cause this thing to rotate this way. So this rotates that way. This is going to go this way. So this is that way. Now my FG is counterclockwise and my toes is clockwise. So this is going to be F toes times R, I'll call it RT, equals FG, and I'll call it RG. And then we go through it the same way. We'd have the equilibrium. We'd have F toes plus F hands equals FG. We'd isolate for F toes in this equation here and sub it into the other one. But what I want you to see here is that we're using the pivot point to eliminate the torque from the hands in this example, so that we could go through and we could solve for toes in this case to find the hands force. I'm not going to do it, but that's the idea. You're going to have an opportunity to do some of these in the homework. We're going to skip example 5. We're going to talk a little bit about this guy here. But again, I'm not going to do this one fully, but we'll talk about this one here, and then I'll give you some questions to do for homework. So it's important to recognize that not all problems require balanced torque and balanced force equations. For example, we've seen this problem before, so we're going to look at it again. 12.5 kilogram ball shown below leans against a frictionless wall. A support cord makes an angle of 8 degrees with the wall. Find the tension in the cord. Now, we could say, okay, well, there's a pivot here. But we did this one before. The object obviously is in a rotational equilibrium. This is true. Rotational EQ exists. Yes, exists. Has an S between the X and I think. Rotational equilibrium exists, but we solve this without torques. If you don't believe me, go back and look at lesson 8, lesson 9 from, well, I guess unit 2. So you don't always need torques. At this point, what I'm trying to do is at this point, we're just giving you tools to be able to solve these things, and it's up to you to determine what tools you need for the problems that are at hand here. And that's where physics really starts to get, where students get unsure of themselves. Like, well, what do I do? There's no obvious one way to do this problem. And it's like, well, yeah, that's where physics gets hard, and that's where you got to get good. So I'm not going to do this example. We've already done this example. You can flip back, but all I wanted you to recognize is that we didn't use torques, and yet we can solve a problem like this. So you, need to recognize the tools that you need to use for the problem at hand. So I'll flip the page. I'll give you now the homework I want you to do. There's a bunch of problems in one. I want you to do all of number 1. I want you to do number 3. 3 is easy. It just asks you to express rotational and translational, both or neither. I want you to do, we're definitely going to do question 4. 4 is good. I want you to do I want you to do 10 and 11. And I'll give you some optional ones here because yeah, they're certainly worth looking at. Um, if you want some extra challenge, take a look at 5 and 6. Both of those are good problems as well, but yeah, for the sake of this, this is what is mandatory. So there you go. If you've got questions, comments, concerns, please feel free to ask. Come on in. I'm available in person. Tuesdays or Thursdays, I'll be available online. So good luck.